Hi folks, welcome to the channel. In this video, we're going to take a look at the Carvera Air 4-axis desktop CNC machine, which Makera developed and introduced to the hobby CNC market around this time last year. Makera is a relatively new CNC startup that launched its first product, the original Carvera, through Kickstarter in 2021, bringing industrial-grade features like auto tool changing and auto leveling to the desktop makerspace. They followed that with the Carvera Air, a more affordable and streamlined version built on that same vision. Like the Carvera Air is a fully enclosed desktop machine with a very robust die-cast aluminum frame with 20mm rails and ball screws for reliable precision, a 200-watt air-cooled spindle, and a max 30 by 20 by 13 cm work volume. And it includes convenient features like a quick tool changer, auto Z-probe and bed leveling, and dust collection and air assist capability, but an external air pump and shop vac is required. A standard 12-volt air pump that you would use for air assist in desktop laser engravers, for example, would work fine. And with the optional chuck rotary and 5-watt laser module, it's capable of 4-axis 3D carving and laser engraving as well. The machine comes with a toolkit loaded with brackets, clamps, and bits so you can secure and work materials like wood, plastic, and composites, single and double-sided PCBs, and even soft metals like aluminum, copper, and brass. It also comes with an emergency stop button, a manual tool setter, safety goggles, cables, a phone or a tablet holder that mounts to the machine so you can control it with a mobile device instead of a PC if you want, as well as a material kit for example projects that Makera put together with step-by-step instructions to help get you started. Makera also developed their own controller and cam software, and a free lifetime subscription is included with the machine. It's shipped 99% assembled, so setting it up is a breeze. Just unbox it, mount the tablet holder, and plug it in. After turning it on and waiting for it to finish homing, I connected to Makera's controller, which I downloaded to my PC. It can be connected via the machine's internal Wi-Fi network, your network, or through a USB cable. Since my Wi-Fi signal in the workshop isn't very good, I chose to connect with a USB cable. The controller interface is user-friendly and provides all the functions that you need to set up and send G-code to the machine. Real-time working coordinates, spindle, tool, and laser status and control are located in the status toolbar at the top of the window. The G-code is previewed in text on the left side and graphically on the right side. The arrow on the right opens a new window for manual motion control. Before attempting to run a G-code, it's a good idea to use the manual controls to make sure everything works fine. More functions for manual control, Wi-Fi configuration, and software and firmware upgrades can be selected in the top right corner, and G-code files can be accessed in the bottom left corner. To demonstrate this machine's functions and performance, I'll quickly walk you through creating the LED display example project before creating a custom project with Makera CAM software. After loading the G-code, you can see it displayed in text on the left side, and the toolpaths are shown on the right with controls to simulate it. The tools required for the G-code are labeled above the preview in their corresponding number. I then clicked the task configuration button in the bottom left corner and followed the instructions in the user manual to set the work origin relative to the anchor position on the workbed, and checked scan and auto leveling to scan the work area and make sure everything is positioned properly, and then probe the material surface to generate a bed mesh of the high and low points so that the controller can compensate for them as the spindle is working. Next, I opened the toolkit and grabbed the bits and some clamps to secure the PCB over an MDF wasteboard on the workbed. The kit also includes a tool for attaching collars to the bits to help make installation quick and easy. With everything set, I clicked the run button to start the job, and immediately the controller prompted me to install the Z-probe into the spindle for scanning and leveling. While this machine doesn't have an automatic tool changer like the original Carvera, loading tools into the spindle using the quick tool changer is just as quick. No wrenches are required. Once the tool is installed, you can either click confirm in the controller or press the button on the top of the machine to proceed. It then scans the work area so you can see the boundary and make sure the spindle won't hit any of the clamps, and then the probe will perform the auto leveling process by taking measurements at the point specified in the task configuration. Once the leveling is finished, the controller prompts to change the Z probe to tool number 2 with an alarm and 2 small LEDs blinking at the top of the machine. I then loaded the 30-degree V-bit into the spindle and pressed the button to continue. After the job was finished, I opened the manual control window and clicked the clearance button to move the spindle to its clearance position so that I could apply the solder mask and prep for the next step. This took around 15 minutes to finish, and it looks pretty good. Next, I used a sanding block to lightly sand the PCB, then applied the solder mask with a syringe and roller, and cured it in about 15 minutes using a small UV light, all of which were provided in the PCB bundle, which does not come with the machine, but it is available to purchase separately. After applying and curing a third coat of solder mask to the PCB, I set up the next G-code in the controller to remove the mask from the solder pads with the provided solder mask removal tool, then drill and cut the PCB to size using the 0.8mm corn bit. The scan margin and auto leveling can be unchecked in the task configuration because that was already performed and saved during the first process. At first, it looked like the tool was just rubbing instead of removing the mask, so I stopped the job to check, but after wiping the PCB with a cloth, I found that it was working fine. This second G-code took around 20 minutes to finish, and everything worked out good. The PCB is still being held in place by a few tabs that prevent it from moving and causing problems when the machine was running, but a small handsaw is included in the toolkit for cutting them. Next, I moved on to milling the ABS base for the display. At this point, I remembered that they had sent a full-size pre-drilled spoil board for the bed, so I stuck one on with double-sided tape before securing the ABS to it. Then I opened the ABS base G-code from the examples folder and set it up in the controller according to the instructions. Because this job will involve deep slotting, it's going to produce a lot of chips. But to give you a better view, I opted to use Air Assist to keep the work area clear instead of using the dust chute. The Air Assist nozzle orientation and the flow rate are both adjustable. In this case, I set it up for max airflow and adjusted it to point directly at the end of the O-flute bit after the controller prompted to install it. This took around 30 minutes to finish. I think the chip load was a bit too aggressive for the length of the O-flute bit, and the final finish pass didn't quite clean up the chatter. But I can get rid of that with a buffing wheel, and overall everything worked out well, so I moved on to engraving and cutting the clear acrylic display. They give you a few options for graphics, and I chose R2-D2 for this demonstration. I left the protective film on the back so it looks a little cloudy at the moment, but it only took 30 minutes to finish, and it turned out great. The last component that had to be made was the aluminum touch button for power and adjusting brightness. A metal cutting O-flute bit is included in the toolkit for this, but for added precaution and to extend tool life, I like to brush a thin coat of WD-40 onto the surface of aluminum when I'm milling it, because it can be finicky and melt, gum up on the bit, and cause a jam when ramping in if your settings aren't dialed in perfectly. I don't think I really needed to this time though. This took 20 minutes to complete and produced a nice finish with no issues. For the sake of time, I soldered the components to the PCB off camera, all of which are included with the material kit so that you can do it yourself, and they include a fully assembled PCB just in case you don't want to do it yourself or have problems when you do. Notice how I control the power and brightness by touching the jumper wire on the end. In order to work properly, this jumper needs to be bent so that it touches the aluminum when everything is assembled and activates the light when you touch the aluminum. It's a lot brighter than I was expecting. I think I should start making my own LED lights for light displays instead of buying them. Next, I tried making a custom smartphone case from aluminum. Makera has detailed step-by-step tutorial videos on their channel showing how to use their CAM software, so I'll just give you a quick rundown on the basics for creating a few different toolpath G-codes in this video. I first drew the model for the smartphone case in FreeCAD in 3 sections. A front and back cover that will be milled from a 3mm thick sheet of 6061 aluminum, and a center section which will be 3D printed with PETG filament. As I mentioned earlier, Makera CAM is available for free for every customer. After installing and opening it, you can choose whether you want to do 3-axis or 4-axis machining with the chuck rotary. When the program opens, you'll see a large preview window in the center right, and at the top of the page, you'll find typical functions like open, save, import, or export image, 2D or 3D files, and Gerber files for PCBs, as well as options for creating 2D and 3D 3-axis toolpaths, 4-axis rotary toolpaths, and laser toolpaths. On the left side, you can select your material type and size, which is best to do before you import any files and start creating toolpaths. Below that is the work coordinate system table that will list your layers and toolpaths that you create, through which you can open and toggle on and off after they're created. To start my project, I exported a 3D model of the smartphone case's front cover in step format and imported it into Makera CAM. I then selected the model and chose 3D Contour Toolpath at the top of the page. A new window opens on the right side that provides options for selecting the geometry and cut settings for the toolpath. To select the geometry, I clicked the Generate Toolpath button, which outlined all of the possible edges that I could use for that toolpath, which I selected by holding the Shift key and right-clicking on them. Then I set the end depth offset to 1mm to make the spindle cut 1mm below the material and into the wasteboard to ensure a nice clean edge. Next, I selected the tool, which was the provided carbide O-flute bit for machining metal. The software already has bits and safe presets for each for you to choose from based on the material that you're working with, or you can tune them yourself and change the tool number in the settings. Next, I selected the inside position so that the spindle will position the bit on the inside of the edge or toolpath instead of on the outside or centered. Next, you can specify whether you want to do conventional or climb milling, ramping, or tabs. I chose climb milling, a 10mm ramp at 5 degrees, and no tabs. Then I click Calculate, and the toolpath was generated and saved in the work coordinate system table on the left. Next, I chose the 3D Pocket toolpath to create the counterbores for the screws that will hold the case together. I then selected the bottom faces of the counterbores, which set the depth of the toolpath, and chose the same O-flute end mill and assigned it the same number. Then I chose the offset path strategy, climb milling around the inside boundary, a 10mm ramp at 5 degrees, and click Calculate to generate the toolpath. Next, I created the toolpath for drilling the screw holes, which can be done with the drilling toolpath or contour toolpath options. To save some time and to stick with the same end mill, I chose to use a 3D contour toolpath and used the same settings as last time. Next, I created 3D contour toolpaths to cut the circle out of the center and the opening for the camera lens in the corner. I kept the settings the same as the previous contour toolpaths, except this time I added small tabs that will be machined to hold the waste pieces in place so they don't get jammed or thrown out of the machine by the spindle after they're cut through. Though you'll see a little later that I made them a little too small for the triangle tab profile, and the center portion was thrown out anyway. The final contour toolpath was for the outside perimeter, and I kept the settings that I used for the previous contour, except I switched the spindle from following the inside of the toolpath to the outside. Next, I selected the 3D chamfer toolpath, then selected the top face that I wanted to chamfer the edge of, and clicked Generate Contour. Then I selected the edges that I wanted to chamfer first, set the chamfer depth to 1mm, which is the max for the provided 3.175mm 90-degree chamfering bit, with an offset of 0.5mm, which will move the point of the bit off to the side of the toolpath by that distance to help cut a clean edge. Next, I created one more chamfer toolpath for the outside edge. Once the toolpaths were finished, I saved the file, clicked Export at the top of the page, and selected the toolpaths that I wanted to include with the G-code. After the G-code was exported, I uploaded it to the machine through Makera controller, opened it, set the working coordinates and auto-leveling parameters, and started milling using Air Assist and a thin coat of WD-40 on the surface of the aluminum, just like before. This turned out really nice. Next, I made the back cover. To save some time, I printed the center part and glued it to the back cover using 2-part epoxy. I decided to make a couple more cases from ABS and polycarbonate as well. Satisfied with how it performs 2.5D milling, I decided to try the 3D relief carving example project next. So I clamped the epoxy sheet that was provided for the project to the workbed, then loaded the G-code in the controller, adjusted the working coordinates according to the instructions, and started the job. This project will be done in 2 phases. First, the machine will rough out the bulk of the material with an O-flute bit, then the controller will prompt to switch to a 30-degree V-bit to carve all the detail during the second finishing pass. This turned out really nice and was amazingly fast, completing everything in just 90 minutes. In my experience with my other machines using Easel Pro and Candle software, something like this would have taken half a day or more to finish, so this is a pretty big change from what I'm used to. After completing the 3D relief carving, I decided to set up the chuck rotary and try 4-axis 3D carving for the first time. I inserted a couple of pins from the toolkit into the workbed, then placed the rotary on top of those for perfect alignment. Then I secured it to the workbed with screws. A couple of epoxy blocks are included with the material kit for this project, and I drilled a hole in the end of one to secure it to the tailstock better. Then I used a square to square the chuck and material with the base as shown before powering on the machine. Just like the previous relief carving, this project will involve both a roughing pass with the O-flute bit and a finish pass with the 30-degree V-bit. This turned out to be another amazing job. It looks like it was sanded and polished to a near satin finish. There are absolutely no tool marks on this whatsoever, and it only took 3 hours from start to finish. Finally, I wanted to test out the laser module. I loaded the image G-code in the controller, set the working coordinates, and started the job. The machine scans the area before prompting you to install the laser module, which is just as simple as installing any other tool. It also has an air assist port, so you can connect it to the air assist nozzle on the spindle for better engraving quality and cutting performance. This took around 45 minutes to finish, which isn't too bad at all, and the dithering looks great. I already have a couple dozen laser engravers of all different types and sizes, but it's never a bad thing for a machine to have more versatility like this. Overall, I'm very impressed with this desktop CNC. Yes, it is relatively small compared to other machines that I've featured on this channel, but it's mighty. None of my other machines can do what this does with the same speed, precision, and quality. I love how solid the frame is, and have no worries about working tough materials like metal with it. With a full enclosure, dust collection, air assist, auto leveling, and more, it has all the bells and whistles that any hobbyist or small business owner would need from a desktop machine. But that's it for this video, folks. In the next one, I'll walk you through how to use Makera CAM to import your CAD design and generate G-code to create your own custom projects. I'll try to get that uploaded for you by the end of this week. Until then, let me know what you think of this machine so far in the comments below. Thanks for watching, and take care.